Brilliant. Well, good morning, everyone. My name is Nick Stewart, and I work in the Digitalised Automation team in our Manchester office. So I do a bit of PLC, HMI, SCADA, but mainly focusing on these future of automation topics. Now, a heavy component in the future of automation is PC-based automation. A lot of the technologies that we're looking to implement in the future, they do run on these sort of environments. So today we're going to take it back to the ground level, have a look at what exactly a software controller is, how it works under the bonnet, and then we'll move into, well, where can we run these software controllers? So we have an offering called the Open Controller, which you will have seen in use yesterday with Chris Jones. But we can also run these software controllers on our industrial PCs. So our range of different form factor industrialized ruggedized computers. Now that spans from the very small one you see in the palm of this hand on this graphic, right through to very large redundant rack mount computers. So we'll have a look at the benefit of running a software controller on one of these as well. Now, the big plus with using software controllers is the ability to write code that can be called from the control system in what we refer to as higher level languages. So languages you'd normally associate with Windows development or PC programming. So things like the .NET framework, or even if you want to go a bit more low level, C++. So we can start to write code in these languages that we can then execute and call from the Step 7 code running in that software PLC environment. Now you'll see a link on this slide. So we do have a trial for the development kit. Unfortunately, there's no such trial for the soft controller itself. But if you do like what you see here in terms of writing some high-level code for a controller, you can by all means have a look at this link afterwards, download it, install it, and have a play around. And we have some examples on our support site as well. So what exactly are we talking about when we're looking at the S7-1500 software controller? So what our colleagues in headquarters development have done is they have taken the firmware that runs inside of the hardware, the standard S7-1500 PLC, and it has been ported to be able to run on top of the x86 architecture. So the architecture that runs in a standard Windows desktop computer. So that obviously means the industrial PCs, like you can see on the right-hand side of this graphic. But if we also want something that's a bit more in the form factor of a PLC, we have the device on the left of that graphic, the Open Controller, which you will have seen yesterday. Now, in terms of engineering these little devices, it's still the same look and feel. So exactly the same behavior as it would be in an S7-1500 full hardware controller. You engineer it inside TIA, you compile your code, and you download in exactly the same way. Now, the software controller, although it runs on a device which has Windows, it runs completely independently, and that's obviously a very important thing, which we'll touch on in the next few slides. Now, the programmers who program the PLC side, they don't need to have a heavy knowledge of Windows. It just comes out of the box, ready to set up, as we'll see in the demonstration. We don't have to get our hands dirty messing around with Windows. We can just do a download straight from TIA. Now, like with all the S7-1500s, we have security and we have protection for the IP baked into these devices way down at the firmware level itself. So all the great features that you're used to with regards to know-how protection or protecting a library or protecting the entire project, all these things exist in these devices as well. Now we have safety integrated on the right-hand side there, because it's worth noting that, as you can see with the yellow flash on that Open Controller, we do have fail-safe variants of these for the IPCs and for the Open Controller itself. Now we can see that we have a number of different interfaces. So the ones that are on the front of the Open Controller are the Profinet. The Ethernet interfaces on the IPC can be used for Profinet comms as well. But if we need more comms, say, for example, a Profi bus connection, we can start to work with CP cards as well. So the compact design is just a reference to the fact that the Open controller does sit inside of the ET200 SP family. Now, why would we look at using one of these over maybe using a full fat hardware S7-1500? Now, at the top, we've got these complex control tasks. So they're fast. Because they're running on the x86 architecture, these software controllers can execute at very high speeds. So we have very short cycle times on these guys. So if we are doing a lot of heavy maths in maybe SCL inside of the controller, we can cycle these things pretty damn quick. Now we've got integration of complex algorithms. So this is referring to if we have maybe written some code in a language such as C to crunch some numbers. Maybe we're analyzing some analog inputs and we want to have an accept or reject signal being sent back. Instead of rewriting that code inside of SCL or anything else inside the controller, we can port the code that we've already written and put it into a function that can be called by these software PLCs. So we have high program and data memory. Now, these devices will actually store data on the hard drive. So you're moving away from having to have a massive SIMATIC MC card if you've got a big program, or if you've got a lot of data logs or a lot of recipes. Now, the integration of the PC applications is obviously where these software controllers sort of stand apart. If you're already in a situation where you have an in-house application developed in, say, C++, C#, VB, and you need to integrate it into a S7 controller, you can now use the development kit to do this natively. So the app that you've already developed in-house, you can run it on the Windows side of these devices, and you can have comms straight in. Imagine a small conduit straight into that S7 controller to pipe data backwards and forwards in next to real time. Now at the bottom, we talk about having the controller, the HMI, and the Windows application all on one device. And you may have noticed on the previous slide that the Open controller did indeed have a DisplayPort connection. Some of the IPCs have a built-in touchscreen as well. What this means is we can have bundles that allow us to run a operator interface, so a WinCC application in the Windows side, and that will directly talk to the software controller. So we've now got just one piece of hardware that's the operator interface and the PLC itself. So reducing space, reducing cost. Now, obviously, we can expand this with all sorts of header modules. Now, interesting one at the bottom, integration of third-party software. So we have seen an application where a USB high-speed camera was connected into the IPC. A software controller was also running on the IPC. And this allowed relatively simple integration to be generated using the development kit. So that comms between that USB device camera in the Windows world going through to the software PLC was happening very, very fast. So we've got a few use cases of why we would maybe want to use one of these controllers and why we would maybe develop our own code to be called from the controller itself. So one example would be if there's a requirement to migrate an existing embedded system. So for example, we still come across systems that run on QNX that are written in C. Now, it would be quite a laborious task to maybe rewrite that entire control system in SCL or ladder or whatever your weapon of choice is. So we would like to look at the software controller as a mechanism to easily migrate other systems that have been written in these low-level languages without too much pain. We're also aware that software to provide simulation, such as MATLAB, can export into a range of different formats. So if you have created a sort of a complex model, you have a mathematical simulation that you've created in MATLAB. Again, maybe if we go back to the example of looking at analog sensors and making a decision as to whether it's accept or reject, we can take these simulations that have already been created in MATLAB and automatically turn them into blocks that can then be executed and called from these software controllers. Now, if we want to run stuff in the Windows environment as well, we can do. And there's a number of reasons this may be advantageous to us, again, over a hardware controller. So a big one is database access. So in this slide, it's talking about SQL, but this could be any sort of database format that can be installed locally or remote. So for example, if we've installed SQL Server onto the IPC, we can then automatically loop back to ourselves for pulling out job records, whatever it may be. But we can also connect over a network through the network interfaces of the device through to databases. So great for if we have a requirement for reading or writing database data. Now underneath, we've got large amounts of data. So again, if we maybe think of an application where we're reading values from analog inputs at very high speed, and we then want to log them to somewhere, and we have a large amount of data that we're logging. If we were doing that with a hardware PLC, it would obviously be a case of using a HMI, but you're not going to get those fast read speeds. Alternatively, with a hardware PLC, we'd be writing it to the MC card, and obviously that's going to reduce its life and fill it up quite quick. So these software controllers are great for this high-speed data logging. We can read the data in at very high speed, and we can start to write it straight to things like CSV files that live in the Windows environment of the software controller itself. Now we can see here with the connection to the computer hardware, so you can understand it's obviously running Windows. That opens like a whole new realm of connectivity for us, integration into Windows networks, or as we talked about earlier on, a connection to maybe a USB camera. On the slide here, it's talking about connection into network printers. So maybe something as simple as an end of shift report being printed. This makes it a lot easier to sort of access a wide array of network printers. Now, at the bottom, we've got complex protocol implementations. So we spoke to a customer recently who had been tasked by their end user to speak a proprietary protocol. Now it's TCP based, and fortunately the end customer was happy to share the spec. So obviously if you're confident you know what is actually being passed over that TCP buffer, it's not too difficult to sort of re-engineer it. Now we did look at using the T-send and T-receive blocks inside the PLC, but as we're all familiar, a PLC is just not designed for string manipulation. It's not what they're designed to do. So it becomes very complicated if you're sitting and writing SCL to handle T-send and T-receive. So these open controllers and these software controllers really do shine when it becomes to connecting to weird and wonderful bespoke protocols that have been derived. Now, in terms of the operator visualization, we've got a nice little graphic of a touchscreen there. So we touched on how we can have these IPCs with a touchscreen on the front. So this slide just goes through how we can interface with these software controllers to give ourselves some operator visualization. And you can see it's quite a busy slide. There's quite an array of ways we can do this. So if we look at the box on the left, local, what that means is what can we install on the device that's running the software controller. So the Windows environment in this example for the IPC. So we can buy these bundled with WinCC Runtime Advanced. So that brings our cost of licensing down. And then on the IPCs, we can also start to install WinCC Runtime Professional and WinCC 7.4 SP1 upwards. So we've now got a nice box in the panel that is our SCADA interface as well as our PLC. And we can see that we can also put WinCC OA on these devices as well. Now underneath, you'll see that's actually the Visual Studio logo. So that's indicating that if you wanted to engineer or had already engineered your own operator interface in a .NET based language, the mechanisms to talk to these soft PLCs would be through OPC UA. So there's a lot of libraries for the .NET framework to make this easy. We've then got through open user communications. So that obviously is covering TCP comms and UDP comms. Or we can use the ODK, which we will come on to later in this slide deck. Now remote, it just behaves like any other S7-1500 would. So what this means is if we had a comfort panel on the same network, we could read and write tags just like we would any other 1500. And the same applies with all our flavors of WinCC. They will all talk to it. If you want to use semantic net, we can still do that. So we can establish the S7 connection to this device over the network and then broadcast the tags in that manner. So let's start to have a look at how this is actually working under the bonnet. So what is happening with this piece of hardware? Because we'll be familiar with an Intel processor booting. You turn the computer on, the BIOS tests itself. It finds the bootloader on the boot hard drive, and then it boots into Windows. So this is the same mechanism with the software controller, but we're doing things slightly differently to keep our soft PLC safe. Now, this slide here, what it's depicting is how Siemens have done this in the past and how we now do it with this new S7 1500 software controller, or not so new anymore. So on the left-hand side of this screen, where it says PC 2003, in 2003, Siemens launched WinAC, which was akin to an S7 400. You programmed it in Semantic Manager, but it was a software controller. Now, these were great PLCs, very powerful, but they had a bit of an Achilles heel, which was Windows XP. Now, Windows XP itself was great. There was just an era of some badly written drivers, so it was not uncommon for Windows to blue screen. Now, WinAC used a piece of software called RTX, and RTX installed itself as an extension to the Windows kernel. So the problem with this setup was WinAC was always vulnerable to whatever Windows was doing. So if Windows blue screened, or if Windows rebooted, or if it updated, you'd lose your control system. And we all know it's not feasible to just suddenly lose the control system. That just can't be. So we moved into 2015 and devised a different approach. So we did away with using this RTX software and used virtualization technology. So virtualization technology allows us to completely sandbox the Windows and sandbox the software controller, and these two guys run completely independent of each other. So if we do have an instance where Windows crashes or reboots, then it's not the end of the world for the software controller. And for those of you that have never come across the terminology hypervisor, you may have used it, but just not realized. So if you imagine software such as VMware, or if you imagine VirtualBox, or if you imagine Hyper-V from Windows, these are all virtualization technology, and these are all actually hypervisors. So what they're doing is they're using a technology that's on the CPU, and this is virtualization technology. And in a nutshell, it allows the CPU to create numerous other virtual CPUs. So you end up in a situation where you've got loads of virtualized CPUs, and each of those virtualized CPUs can then boot into a whole new operating system. So the one that we're all familiar with will be the Type 2 hypervisor. So you get your laptop out, you turn it on, it boots into Windows, you then fire up VMware, and then you boot into your XP VM, whatever it may be. So that's obviously great for us, but in terms of a soft controller, it's not great because you've got that additional layer of that initial boot to Windows added. So we use the one on the left, which is called a Type 1 or a bare metal hypervisor. So for those of you that have come across ESXi, that is an example of this. So the computer turns on, and instead of booting into Windows, it boots into this bespoke Siemens generated hypervisor. And then from there, it boots up into two different guests. Now, the reason why this is good for us is it allows us to have the software controller accessing only certain parts of the hardware that we want. So if we imagine, for example, an IPC that maybe has 3 network adapters, we can exclusively assign use of those network adapters either for Windows, or we can assign it directly to the software controller. So in terms of security, this is a great way to keep these separated. Now, how this happens in effect is when we turn on any device that has the software controller installed. So this is the same principle for the IPC based offering and the open controller device itself. What we're greeted with is this custom boot menu, and the boot menu is basically giving us two options. Now, if we select the option for Windows only, what happens is on the hard drive, we just load the Windows bootloader and Windows boots up as it would on our standard desktop computers. Now, if we choose the Windows and the software controller, which is the standard option, the Siemens custom hypervisor is started. And when the Siemens hypervisor starts, it creates two virtual machines. So one of those virtual machines is a VM for Windows, and the other one is a VM purely for the software controller. And the way this works under the bonnet is a chunk of RAM is taken for the work memory of the PLC, and one CPU core is taken for the PLC. And the rest of it is then presented to Windows. Now, we talked about earlier keeping the software controller safe. So as we said, if Windows needs to be rebooted, then we can reboot from the start menu and it'll appear like a full system reboot. But really what's happening is it's just that virtual machine restarting where Windows lives. The whole computer itself hasn't restarted, so we're not losing the software controller. Because obviously this is a very, very critical thing with using software PLCs. So obviously the same thing applies for Windows updates, and the same thing applies for if it unfortunately blue screens or crashes for whatever reason. Now, obviously this is helpful if we have a UPS in the system, and we can see at the bottom, if we trigger a shutdown from Windows, then it will take everything down and it will gracefully control the PLC as well. So a restart will just reboot Windows, but a shutdown will close the whole thing down and power it off. Now, we talked about large amounts of storage. So what we can do with the software controller is have an area of the Windows hard drive dedicated for the storage of things like user files. So if we're using the function blocks inside the PLC to read and write data to the simulated MC card as such, we can do that. The actual program itself lives there, the archives and the recipes, and we can store all these on the hard drive of the computer itself, so giving ourselves a much larger area for storing data from the control system program. Now, when it comes to communications, we have a range of mechanisms to do this. So the first network interface at the hypervisor level is always given to Windows. Now, on the left-hand side of the slide, we can see that that allows a certain level of external communication. So we can access a number of different things through Windows and then route through to the software controller. So you'll see there that we can do our downloads, we can do S7 comms through this network adapter, but we can also start to do things that rely on the TCP blocks. So we got Modbus down there and we got the OPC UA. Now, the same thing applies for any subsequent network adapters, because once we get into TIA in a moment, you'll see that we have the choice of what exactly we want to do with the rest of the network adapters. And what this means is we're actually configuring the hypervisor, and we're telling the hypervisor, do we want the other network adapters to be given to Windows, or do we want the other network adapters to be given to the soft PLC? So we now have the choice of basically saying, maybe I want two network adapters in Windows because I'm on two different networks, or maybe I want to have two different Profinet adapters. So maybe I'm straddling two different Profinet networks for whatever reason. Now, a nice feature with these software controllers is they have a virtualized network adapter. Now, if you've ever used again, VMware or VirtualBox, you may have noticed that host-only adapter that allows you to do comms between your PC and the VMs that are running, but it's not actually going outside your computer. It's not going anywhere external. So what we have in this software controller is very similar to that. So what happens at the hypervisor level is a virtual network adapter is created and exposed to Windows, and then a virtual network adapter is created and exposed to the PLC. So we've now got a direct simulated Ethernet cable between our Windows environment and our software PLC. So we can have a look at setting that up as well. So this is great if we want to do things like access the JSON web API from inside Windows, or if we want to access the web server from Windows, or if we want to do anything that's TCP UDP based, when we can obviously do things like accessing the OPC UA server. So maybe we've got some sort of third-party application that talks over OPC UA. Nice and simple to integrate that into the Windows environment. Now, this is a busy slide, so we'll just touch on it very briefly, and it's important to know. If you go and look inside of TIA Portal, you'll notice that the very latest version of our hardware CPUs is version 2.8. Now, you'll then notice that the latest one for the software PLCs is 20.8. Now, there's a bit of confusion as to why that's happened, but the reason behind it was our product management in headquarters wanted to keep the naming convention and the versioning of the software PLC and the hardware PLC identical. And this was the case. So we had 2.5 for the soft PLC and the hardware PLC. Then we had 2.6 for both. And then there was a massive update for the software PLC. And it was judged that it was so big, it should be up-revved. So the software PLC was updated to 2.7. But no 2.7 ever came for the hardware controller because it just wasn't applicable. So we then had a situation where the software PLC was 2.7 and the hardware PLC was 2.6. So obviously questions were then raised. Why is it 2.7? Why do we not have the 2.7 update for the hardware PLCs? And there wasn't any reason because there was no additional functionality. So we needed a way to differentiate between a hardware PLC and a software PLC. So all sorts of possibilities were looked at to adding an additional digit to these version numbers. And this weird V20, it all comes down to the Profinet standard. The Profinet standard will only allow you to have 2 decimal points, and the Profinet standard will only allow the last 2 digits to be 1 character long. So you can kind of see one place where you can bung a number, and that is in this first section here. So if you ever see a 0, all that's indicating is it is version 2 point whatever or 3 point whatever. It's just indicating for you that that's actually a software controller. So hopefully that's cleared up some confusion in regards to why has it got suddenly jumped so far into the future. Now what we'll do now is we'll jump out of that and I'll quickly show you what it looks like on the computer itself. So over here, I have got an IPC that is running the software controller. So I've just powered it on and I've got to this boot menu. So by default, this would normally time out and select this option for 3 seconds, but just wanted to demonstrate what it looks like. So we're going to go ahead and select the Windows and soft controller and allow it to continue its boot sequence. You can see there that the hypervisor has now started itself up. So it's creating those 2 guests in the background. And once it has created those guests, we'll start to boot Windows just from the standard Windows bootloader. And we'll never actually see the software controller again. It will just run completely headless, completely independent from the Windows environment itself. The reason why that option does exist is for patching and updating the software controller. So obviously we don't want to be patching and trying to write to files that are already running. So if you do find yourself working with a software controller and you download one of the patches from the Siemens support site, always make sure to fully power the thing off. And then when you turn it back on, you'll be presented with the screen we just saw. Pop it into Windows only mode, and then you will be able to patch it. So we can now see that this one's actually been preloaded with WinCC Runtime Advanced. So obviously allowing us to have the ability to make this guy our interface as well as our controller. Now, if we have a look at how exactly we can we can work with the software controller from the Windows environment. We can see down here in our system tray that we have this icon here. So if I just zoom in for us to make this a bit more legible, let's do Control 4. We can see down here we have this software PLC icon. Now you'll see it's got a green banner around it, and what the green banner tells us is the PLC's in run. So this is a very easy way to get an indication of the status of our controller. So obviously that will be in yellow and it will be in red depending what other status we have our system in. When we double click that, or if we double click this icon on the desktop, we're then presented with this little window here. So for those of you that are familiar with the front screen of an S7-1500, it's exactly the same setup. So all the functionality and all the feature that front screen has, we now have it available as a little Windows GUI tool. And what this little tool's doing is it's actually communicating through to that other virtual machine and getting the real-time information about how the software controller is behaving. So you can see all the information with regards to things like the diagnostics and see what the status of the controller is. Now, if we wanted to write ourselves some sort of batch file, if I just run this that I've got here, and if we quickly zoom in, we'll be able to see on the right-hand side, if I move my mouse, whoops, we actually have a command line shell tool called CPU_control. And using this, we have a number of different switches, so we can power off, power on, put it into run. So if for whatever reason we did want to have a scheduled task, or if we did want to check the status of the controller way down at sort of a command prompt level, this is something we can do. So if we come out of this now and we go and have a look at how we actually configure these devices. So we'll quickly look through the slides here and have a look at what can we run this on. So we'll fire this back up here. And the first offering we can look at is the Open Controller. So we've looked at what the software controller is. We're now going to have a quick look at what we can actually run a software controller on, what hardware. So the first one is the Open Controller 2. So this is the unit that you will have been shown yesterday by my colleague Chris. And we can quickly just jump forward to this nice graphic of it here. So the nice thing about working with the Open Controller is on a first glance, it doesn't look like a computer. So the thing when you look at it, it just looks like an ET200 SP PLC. But when we look a bit closer, we can start to see obviously the telltale signs that this is actually a computer, things like USB ports and display ports as well. Now, in its own right, it is quite a powerful little computer. So we can see here it has a quad-core processor in it with 8 GB of RAM. You can see on the front of it, the blue USB slots are actually our USB 3 and they are powered. And the whole device runs on a CFast card. So on the flap on the right hand side, we can open this up and we can remove that card as we require. So in the top left hand corner of the device, we have the display port. So this is where we could hook up our external monitor. Underneath that, we have our USB ports. And then at the bottom, there is a gigabit Ethernet connection. And this is the connection that is given to Windows. So this would maybe be the connection for engineering or connection to a customer's network. Now, these little devices take all the bus adapters that exist in the ET200 SP family. So we can clip on all sorts of things on there. So our RJ45 Profinet adapters or any of the other ones that exist in the family, depending on what kind of communication we are doing. So in the middle of this graphic, you can see it's got a nice big set of heat fins on it. So the thing is passively cooled. There's no fans in it at all, which is great for sticking it in a cabinet. We all know that a fan in a cabinet will get covered in dust, it'll slow down and it'll eventually fail. So having this as a completely solid state device with no removable components is really good. Now on the right hand side, we have that little door, and the little door is what opens and exposes the CFast card. So if you've not come across CFast, it is the successor to Compact Flash. So it's a little small SATA-based device, which is in essence a self-contained little flash-based hard drive. So again, no moving parts in it. And the nice thing about it being on a flash card is if for whatever reason we did have a failure of the controller, some damage, we could just take out the CFast card and pop a new one, or pop a new open controller in, pop the CFast card in, and we could reboot and be straight back into service. Now it's worth noting that at the bottom of this, you can see there's an SD card slot. That isn't a Somatic MC card slot, because as we saw earlier in the slides, all the hardware configuration is actually stored on that CFast card itself. So that is actually an SD card reader, which is purely for Windows. So if we are data logging in Windows, we can have an SD card popped into that slot there. Now we've got our standard run stop switch, and we're running this thing on 24 volts. On the right hand side, you can also see that we have the ET200SP. Because this exists in the ET200SP family, all the ET200SP IO are available to clip on the side of this. So earlier on, we talked about a use case of maybe high-speed data logging from an analog input card. You can now see where this would really come into its own with that. So in terms of the operating systems we can get on these open controllers from ourselves, we ship this with Windows 10 Enterprise LTSB. So it's important to have the long-term service branch of Windows on these devices, because as we'll all be familiar with Windows, it does have a habit of updating itself, and features get added and features get removed. And this isn't really something that's applicable in a sort of an industrial application. So the LTSB is a version of Windows which stays as it is. It's set in stone, so the version that it behaves like when it's issued is the same throughout its life cycle, and it's supported for up to 10 years. It is patched, but only security patches. So there is no features added or removed, because obviously that may be a problem. If we're using some of the functionality in our own applications we deploy, we don't want them to be changed. Now, all the security settings are enforced on there for you. So the build out the box is already quite locked down with a number of policies, and an initial commissioning wizard will help you and set that up for you. Now, a new feature we have is the ability to run Linux on these devices. Now, the Linux is not provided for you. So how this happens is you choose your own flavor of Linux and you install it on the controller itself. So the ones that we've tested in-house is Debian, so versions 9 and 10, but you can install different versions of Linux on there as you wish. So what this means is we can now have a device which is still our software controller, but if we have an application that's written for a Linux environment, or we just want the Linux for the extra speed, we can deploy Linux in lieu of the Windows 10 on these devices. Now, the initial setup of the Linux is slightly different from the Windows, because there's so much variant in Linux. When you're provided with one of these Linux-ready open controllers, there isn't actually an operating system on it. So as you can see from the graphic in the top left, it's configured with the hypervisor, it's configured with the software controller, but it's got a big blank space on the rest of the hard drive for you to install whichever version of Linux you want. There's then a set of drivers to set up things like that virtualized network adapter we discussed earlier. So you still have that connectivity between the Linux environment and the software controller itself. Now, if we want a bit more horsepower, if we need a faster processor, then we are moving into the realms of using an IPC instead of an open controller. And there's pros and cons for doing this. So obviously the main pro for this is the additional speed. Maybe we want just more RAM and more CPU that is offered for the open controller. But the massive drawback and the massive con for moving into the realms of IPCs is we've straight away lost the onboard I/O. We've straight away lost the small form factor. And there's still customers who don't like opening a cabinet door and not seeing a PLC there. It's still frightened by opening a cabinet door and seeing a PC. So if we do go down the route of using it on an IPC, the software controller is available for quite a few IPCs in the IPC product family. So the two on the left, or the two families on the left, are our embedded devices. So these are the ones that are completely solid state, completely fanless, and designed to run inside cabinets for very long periods of time. So we have the 227 and the 277. And the difference between those is one has an integrated screen on it and one does not. And the same applies with the 427 and the 477. So the same computer, but with a touchscreen bolted on the front. And the benefit of the touchscreen being stuck on the front is we can now have the operator visualization all in one device. If we need more performance, then we're looking into the realms of having a rack PC, and that is obviously what we are showing on the right-hand side there. So it's horses for courses when selecting between a touchscreen IPC and just a box-based one. If we maybe want to have a completely self-contained solution, we have a small piece of machinery, or we just want to stick it in the cabinet door or in a console, it's nice to have everything in one box. But if this is a bit of a larger machine and we're in the realms of having a distributed control system, then we want to look at maybe using the box PC instead, because this allows us to piggyback onto networks and start to connect to things like comfort panels, or connect to things like flat panels, or even drives and Profinet IO that we have out there on the system. So I won't dwell on this. It's just a specs page of what we have available for these IPC 427Es, and just a really quick graphic to show what the 427E looks like on the base. On the base of these 427Es, we have a range of connectivity. So you'll see again, it's 24 volt powered. We've now gone up to having 4 USB 3s. We've got a CFast slot there. It's worth noting these don't necessarily run off the CFast, but they can. So they normally come with a SSD drive inside them. We've got the 4 LEDs on this, which is important because when we configure our software controller, we can actually use those LEDs to give us an indication of the health status of our device. So things like if the PLC is in run or if it's in stop, the same as we would on the front of a hardware controller itself. Now we've got the 3 gigabit LAN on this particular model, and this is where we can say X1 is Windows and X2 and 3 are maybe my Profinet interfaces or whatever arrangement we can have. And we can also get these with serial ports. So if we do have a requirement for legacy comms, we can do that. Now, one of the big deals with these IPCs in comparison to an open controller is there is no ability to do isochronous real time. And the reason behind that is because these 3 ports here are actually Intel based. So they're not true Profinet controllers as a hardnet controller as such. So it is completely softnet, so it's not actually capable of achieving the isochronous real time. But what we can do is get a variant of this 427E that does actually have some PCI expansion, so 1 or 2 slots. And then what that does allow us to do is use things like the CP1625. We can then hook that up to our IPC, and then we can have ourselves some isochronous real-time comms coming straight out of these software controllers. So we'll quickly jump into TIA and we'll have a look at how we configure one of these guys. So we're going to hit up add new device, and then in the middle we've got this PC systems. So you will need step 7 professional installed in order to configure these. So we see we've got the open controller. It's nice to work with the open controller because it's a fully self-contained hardware object with minimal configuration. You'll see we've got the Fs, the Ts, and the TFs, and we've also got the ones bundled with WinCC Runtime Advanced, so that the connection and everything is already configured for you. So the one I'm working with now is obviously the IPC, Industrial PC. We've got a box variant. We have a 427E. And we have one with the 3 network interfaces on it. So we'll pop that into the project like so. And then once we've added our software controller as well, it's exactly the same as engineering any other S7 1500. So on the right hand side of the screen, I have the options of what I can drag onto this, because you obviously understand that this could be a SCADA box, it could be anything, but in our application, it's going to be a soft PLC. So we find our S7 1500 software controller, I have got a 1507 failsafe. Click that one, and then we can just drag and drop that into this available slot here. Now, the next thing we need to do is quickly parameterize up these Ethernet ports. So we've got 3, and as we discussed at the beginning, we need to determine what we are going to do with those. So click them once at a time. So interface assignment, let me say this one goes to Windows, so that's part of the download. The second one, interface assignment, I want this to be part of my software PLC. So that is now a Profinet interface inside the controller. And then let's make this X3 one as well. So we now have a 1500 in essence that has 2 Profinet interfaces. We'll just make sure that the Ethernet address here matches what I actually have in front of me. So it is actually 1.12, and we can save that. And let's give it a compile. Hopefully everything's happy. And we can download that to the controller. So if I click here, trigger my download. Being a bit bad here, I'm downloading over a Wi-Fi adapter. And then we can do a start search, and we should hopefully find our IPC427E with the IP address of 1.2, and there we go. So it's identified it as a 427E, and we can click load. So we click yes, and we should start downloading to our controller. So while that's happening, we can just look here quickly, and what we will see in a moment when we are looking at the IPC is we'll have a window appear to tell us that the computer is receiving a new hardware configuration. Because what you have to imagine at this point in time, the hypervisor hasn't been configured to do anything. So these X2 and X3 adapters by default have just been given to Windows. So we'll click load. And then we should see the configuration is being absorbed into the system. Now, because this is such a drastic hardware change, we need to reboot the computer because the hypervisor needs to jiggle about these network adapters and move X2 and X3 to be in the other virtual machine, which you must appreciate can't be done while the virtual machines are running. So this will now restart. And if we minimize this for now, TIA gives us the option to say, I'll wait till the computer restarts. So we'll click finish and we'll leave TIA waiting for the time being. While that's doing it, we'll have a look at the Open Development Kit. So the Open Development Kit is our mechanism for generating functions that can be called from the PLC logic in these higher level computer programming languages. So computer programming languages such as C#, the Visual Basic, and C++. So the C# and the VB is basically anything that will run on top of the .NET framework. Now, when we want to engineer one of these ODK functions, we need to purchase the Semantic ODK add-on. And when we install that, we get a free development environment called Eclipse. But if we want to do that development for the Windows environment, we need to have a copy of Visual Studio installed as well. And what will happen when we install our development kit is Visual Studio will then have a number of templates in it to basically handhold us on the path to making our own ODK functions. And obviously it goes without saying, we still need to have TIA Portal on our engineering box because we still need to download the configuration to our controller. Now, in terms of the runtime, so the devices themselves, we obviously need either an IPC or an open controller. And then we don't need to worry about anything else. The Open Development Kit runtime is actually baked into the software controller out the factory. It's not an additional license. There's no tick boxes or anything you have to do in the controller itself. So we just power up the controller and we are able to start to deploy these ODK functions. Now, there's 2 types of ODK functions, and the difference is quite drastic. So if we just cast our mind back to the beginning of the slide deck when we looked at that hypervisor, and we looked at those two virtual machines, and we had a virtual machine in Windows, and we had a virtual machine for the soft PLC. The difference between these two ODK types is one executes its code inside of Windows, and the other one executes its code inside of that virtual machine where the software controller runs. So there's pros and cons for both, or not pros and cons. There's reasons why you would use one over the other. So if we were triggering our logic to run inside the PLC, this would be for things like closed loop control, or if we've got a pre-written algorithm, or if we are crunching some numbers and we need a response very quickly, we would use this functionality, so bake it into the software controller virtual machine. On the other hand, if we maybe needed to connect to a web service or a file share or a SQL database or a network printer, all these sorts of things, we need to use Windows for these. And you can imagine these aren't necessarily time critical. So if we have a look at how this executing happens, we've got this slide split down the middle. On the left-hand side, this is how these ODK functions are executed in Windows. And on the right-hand side here, we have how these ODK functions are executed in that software controller VM. So the big difference is whether it's synchronous or asynchronous. So the Windows ones are completely asynchronous. So if we call an ODK function in Windows, what basically happens is it gets chucked on a stack, and then it's executed in Windows. And when Windows has finished doing its thing, it reports back to the PLC what the result of logic was. So the key takeaway for this is the PLC scan is not being hung up on what Windows is up to. They're running completely asynchronous. Now, obviously, if we're looking for an SQL connection and it times out, we don't really want our PLC scan to be hung up by this. On the other hand, if we're evaluating lots of analog inputs, so we want an accept or reject before the canister or whatever it is goes out the end of the line, this is where we really want some synchronous programming. So on the right-hand side, this is the execution of the blocks that run in the virtual machine for the software controller. So you can see here, it's very similar to how the calling structure of a organization block would be if it was calling any other standard PLC code. So we call our ODK and we wait for it to give us a success result before we continue with our scan. So you can obviously appreciate on this right hand side here, if we were trying to connect to something, then this really isn't the approach that we want to take. Now, with regards to security, it's very important to note that these ODK functions, although they live inside the virtual machine for the controller, are completely sandboxed. So if there's any badly written code or even malicious code, there is no way that it can leak out and cause havoc within the controller itself. So completely executed inside of a sandboxed environment. And again, on the Windows side, it goes without saying, having those two virtual machines, it's just security by design. So what is running in Windows can't harm what is running inside of the software controller itself. So if we have a quick look at the sort of deployment of these ODK functions, what we'll do now is we'll deploy one that runs in the Windows environment just to give you a quick example of the look and feel and how simple it is to deploy these applications. So I'm going to fire up version of Visual Studio. And then when we fire up Visual Studio, we can click File, New Project. So on my computer, I've installed the Open Development Kit, and you'll see for the different programming languages that are installed on my Visual Studio instance, we have these different standard templates for ODK functions. So I'm going to do it in C# today. So my ODK block, we'll give it that name, and then we'll click OK. Now, similar to TIA, we have the project tree on the right-hand side over here. So I don't know if we can maybe zoom in, make that more legible. And it looks quite busy, to be honest, to begin with. But most of what's here, we don't need to worry about. There's only 3 files that really concern us. It's the definition file. So what we're doing is we're telling the Visual Studio compiler what function blocks we want to allow access to inside of the Step 7 environment. This will become more apparent in a moment. We then have the source code. So this is the computer-based language that's going to execute in Windows when these functions are called from the PLC. And then at the bottom, the compiler makes us some SCL so we can automatically generate the blocks that invoke these commands that execute in Windows. So if we go into the definitions file first, there are a lot of comments here. And what this is just basically doing is it's helping us to determine the difference between the data type in the Visual Studio world and the PLC world. So a big example being integers. On a computer, they're normally 32-bit, but we're used to in the PLC world still working in 16-bit numbers. So we'll go down to the very bottom. We'll scrap out the default one. And all of these ODK functions always have to return an ODK result. And in C# or any C language, we always declare the result, the data type first. So the nice thing about the ODK result is we can start to define custom error messages and success messages. So you'll all be familiar with the status pin on the back end of the vast majority of the blocks in TIA. So for example, if you're trying to do a TCON, you'll get the 7000s, the 0000s, and then the Fs in hex for whether the function failed or succeeded. So what we can do is we can start to define our own, or we can just use the default one, which is 0. So 0 indicates that we finished correctly. So if I make a function called basic addition, open it, we now declare to the compiler what kind of pins we need. So you'll be familiar with TIA. You have your ins, your in-outs, and your outs. We can use all three of those data types. So we'll now say what the data type is in TIA, and then we'll just give it a name, something that's relevant to us inside the Visual Studio. So I'm just going to do some basic arithmetic. I'm going to have myself 3 integers, 2 inputs and 1 output, and then we can very simply do some logic with this. So if we zoom out, we can hopefully give that a quick spin of the compiler, and the compiler should hopefully generate the interface for us. So at this moment in time, the compiler is going to fail because it's saying I can't find any C# to go with that. So this is when we come into that source file, and I'll quickly remove the default one. And this is where we would start to chuck in our C#. So there's a few different functions in here by default. So we have onLoad. This is when the ODK function is loaded into the memory on Windows. So we can do triggers here, but by default, nothing occurs. So maybe if we want to log when this ODK function was loaded. And then below, very useful ones, OnRunOnStop. So we can start to handle event triggers. So when the PLC is put into run, we could maybe log to a SQL database, and likewise with onStop. So they're the ones that we get out the box by default. We're going to use Visual Studio's helpful tool for inheriting functions. So implement the interface. And if we go down here and I zoom in again for us, you can see I've got my basic addition. So this is tallying up with that definition. So just for ease, I'm always going to return success because this is the status pin. We can return our error messages if we wish, but we'll just keep this nice and simple. So we'll create a result, which is equal to integer 1 plus integer 2. And then we will make that the result. So we need to convert that to a short. And there we go. Some very, very basic arithmetic, but it's being executed in the C# inside of Windows. So if we save this and compile it again, this time you'll see that the compile has succeeded, but you'll also see above that, we can see we've generated this dynamic link library. And this is the library that we just made with all our executable C# code. So this is what we need to go in a minute and deploy onto our IPC. But for now, we're going to look at that third file on the right that I discussed. And this is our SCL. So this is what we want to use in TIA to generate the blocks to call this, these functions. So if we hop back into TIA, we can just fire up our PLC. And then on the left-hand side, you may have a point to notice we have this external source files. So if we go in here, we can go add new external file, point it to that SCL file that Visual Studio created for us. And you'll see at this moment in time, we just have our main and we have our safety, and we can right click on here and we can do a generate blocks from source. So yes to overwriting UDTs if they exist. And we have load and unload, because what we're doing there is telling Windows to load the DLL and unload the DLL if we don't need it anymore. And you can see we've got our basic addition block. So we'll quickly chuck in an interface DB to allow us to call these. So we need to load the DLL. We may need to unload it. We need to request the addition. We need an integer 1, a 2, and a 3. Let's have some statuses because we want to see these in hex. So if we just go through and say int, if we drag this guy down, overwrite. And then if we say word, because we want the base 16, overwrite this as well. And then if we come into our main, now normally you do something like in the startup OB, unload and reload, so it's fresh, but just for sake of demo, we will chuck them into our main OB scan. And again, we'll put the load, we'll put the unload just in case we need to flush it. And then underneath, we'll have our basic addition. So the key takeaway from this bit is the code isn't executing inside the soft controller. This is purely to call the Windows environment to jump into action. So if we go here, we want to, if I scroll up, we want to load. We want to put a status on that. We want to unload and put another status on that guy. And then finally, we want our integer 3, our status 3. We want our integers 2 and 1. And we want our request pin of this. So if we give this all a little spin of the compiler, fingers crossed we get a clean compile. It looks good. Let's poke this down to the unit. And now we don't want to trigger that DLL load just yet because there is nothing to load right now. So we'll get this online just so we're all prepped and ready to go when we come back. And we'll now quickly jump onto the IPC again for the purpose of deploying our ODK function. So if I back into my Visual Studio, if I right click and go open folder in File Explorer, I should be able to poke around and find my DLL. So I'm just going to copy that onto the clipboard using remote desktop this time, back into the IPC, paste it onto the desktop. I've got a shortcut to this directory. We'll remove that because we don't need it anymore. And what happens with this directory is Windows scrapes this directory for DLLs, and Windows also listens to the software controller. So if you imagine this is the conduit for the DLLs that get loaded. So if we pop this into here and click continue, we now have our new DLL containing all our C# code ready to be controlled from the PLC. So now at this point, we can go back into here. And if all being good, our 7,000 should change to our ODK success, which if you recall was 0. So we'll double click this. And we can see there we go, we've got our done pin and we've successfully loaded. There's lots of error messages built into this. So for example, we get a 7100, which tells us that it's already loaded if we try to load it again. So we don't need to unload it right now, but what we want to do is pop some values into our integers. 1, 2, 3, and then we can put 4, 5, 6, and then we can request. And we can see here that we've got the done, and we can see we got 5, 7, 9. So very simple, but the key takeaway from that is what you've just seen happen there is being done in the C#. And because the .NET framework is obviously so powerful, the things built in like SQL connectivity, we've got things built in like HTTPS connections. This opens up a lot of avenues with regards to taking code written for a Windows environment and programmatically calling it from the PLC world. So I've overrun by 5 minutes, but I will open it up to questions now. So if anyone has any questions on what they've seen, or if you'd like extra clarification on anything, please feel free to shout now.